The cable-stayed roof lift for Victory Arena in Volgograd, Russia, was a highly intricate process involving the sequential assembly of the roof's structural components. The process included the precise lifting of upper and lower tension rings, installation of cantilever beams, and a final lift to secure the roof. These components were then connected to a compression ring, ensuring structural stability. The first big lift of the upper tension ring was a critical step in the Victory Arena roof construction. This phase involved carefully lifting and positioning the upper tension ring, a key structural element designed to stabilize and distribute loads across the cable-stayed roof. Accurate alignment and tension control were essential to ensure the ring's integrity and overall structural balance. The installation of the cantilever involved attaching large, projecting beams to the upper tension ring. These cantilevers extend outward, forming the main framework for the roof. Each segment had to be precisely aligned and secured to ensure even weight distribution and structural integrity. This step was vital for creating the expansive, column-free roof design. The transfer of jacks between upper and lower lugs involved repositioning hydraulic jacks to shift tension forces from the upper lugs to the lower lugs, stabilizing the roof's structural elements during the lift. The second phase big lift involved raising and positioning the lower tension ring, enhancing the roof's stability and load distribution. The final big lift was the culmination of the cable-stayed roof assembly at Victory Arena. In this phase, the entire roof structure, including the tension rings and cantilevers, was carefully raised to its final height. This complex operation required synchronizing multiple hydraulic jacks and monitoring stress points in real time to maintain stability. Once the roof was elevated, final adjustments were made to ensure precise alignment with the compression ring. This lift marked the successful completion of the structural framework, creating a stable and balanced roof for the stadium. The connection to the compression ring was a crucial final step in the roof assembly. It involved securing the upper and lower tension rings, as well as the cantilever beams, to the central compression ring. This ring acts as a stabilizing force, distributing the roof's weight evenly. Engineers carefully aligned and tensioned cables to achieve a balanced, load-resistant structure, ensuring long-term stability and durability. The Osman Gazi Bridge, Osman Gazi Köprüsü, stands as a remarkable feat of engineering and a pivotal piece of infrastructure for Turkey. Spanning the Gulf of Izmit, the bridge connects the cities of Gebze and Yalova, shortening travel distances and significantly improving transportation across this region. At 2,620 meters, 8,600 feet long, this suspension bridge was opened on July 1, 2016, becoming the then longest suspension bridge in Turkey and the fourth longest in the world by the length of its central span. Although its global ranking has since dropped to 7th, with newer bridges like the Çanakkale 1915 bridge surpassing it, the Osman Gazi Bridge remains a vital landmark. This comprehensive account traces the timeline of the bridge's construction, the challenges faced, and its impact on regional connectivity. The construction of the Osman Gazi Bridge was part of a larger project, which aimed to enhance the transportation corridor between Istanbul and Izmir. The contract for the bridge and the Gebze-Bursa Highway was awarded to a consortium known as NOMAYG JV in 2009. This joint venture consisted of 5 Turkish companies: Nural, Ozalton, Makyal, Yüksel, and Göke, and the Italian construction giant Astaldi. The entire highway project, including the bridge, was estimated to cost around 11 billion. Construction began with the groundbreaking ceremony on March 30, 2013, led by then Prime Minister Recep Tayyip Erdogan. The strategic goal of the bridge was to reduce the distance between Istanbul and Izmir by about 140 kilometers, 87 miles, miles and shave travel time between these cities from 6 hours to approximately 5. This 420 kilometers, 260-mile stretch included 3 lanes in each direction, providing a smoother and quicker route for travelers and commercial transport alike. The plan initially included 2 lanes for a high-speed railway running through the middle of the bridge. However, this was eventually discarded in favor of adding a 4th lane for road traffic. This change stirred some controversy, with critics suspecting the decision was influenced by automobile lobbyists. The construction of the Osman Gazi Bridge was awarded on an EPC, engineering, procurement, and construction basis to the Japanese firm IHI Infrastructure System Co. The company was no stranger to large-scale bridge projects, having also been involved in the construction of Istanbul's second Bosphorus Bridge. The detailed design work was subcontracted to the Danish engineering firm COWIAS, which collaborated with Dissing plus Whiteling to ensure an aesthetic design. On January 2013, IHI received the notice to proceed, and the expected total project duration was set at 37 months. The bridge has a main span of 1,550 meters, 5,090 feet, and 2 side spans of 566 meters, 1,857 feet each. The towers, towering at 252 meters, 826.8 feet high, were designed to withstand seismic activities due to the region's earthquake-prone nature. Additionally, a clearance of 64 meters, 210 feet was provided to allow uninterrupted marine traffic beneath the bridge. The construction required 34,000 tons of steel, sourced from Liberty Galati in Romania. The scale of the project posed various logistical and engineering challenges, from designing sturdy towers to managing the massive steel components. On March 21, 2015, a significant accident occurred on the construction site. During windy conditions, a catwalk installed in February 2015 broke away from its bolted joint cable on the south tower and fell into the water. Catwalks are temporary walkways used by workers to access different parts of the bridge under construction. Fortunately, no workers were harmed, as the section was temporarily closed due to adverse weather conditions. Nevertheless, the incident required the suspension of marine traffic in Izmit Bay for security reasons. Operations resumed on March 23 after the fallen catwalk cable was recovered and the situation stabilized. Despite the accident, the bridge construction continued as scheduled and reached its completion by June 30, 2016. The opening ceremony on July 1, 2016 was a significant event in Turkey, marking the achievement of constructing the country's longest suspension bridge and one of the longest in the world at the time. Upon its inauguration, the Osman Gazi Bridge and the O5 motorway cut the journey between Istanbul and Izmir, easing travel and bolstering economic and social ties between these cities. The bridge's opening also signified a notable technological and infrastructural achievement for Turkey, as it stood at the forefront of modern engineering projects in the nation. The Osman Gazi Bridge's impressive design includes several notable specifications. Main span length, 1,550 meters, 5,090 feet. Side spans length, 566 meters, 1,857 feet. Clearance, 64 meters, 210 feet. Tower height, 252.0 meters, 826.8 feet. Deck size, 35.93 meters times 4.75 meters, 117.9 feet times 15.6 feet. These specifications underscore the scale of the bridge and the engineering prowess required to erect such a structure in a seismically active zone. In the years following its completion, the Osman Gazi Bridge maintained its rank among the world's longest suspension bridges until the inauguration of newer bridges like the Canakkale 1915 bridge. This newer bridge, opened on March 18, 2022, across the Dardanelles Strait, took the title of the longest suspension bridge in the world by central span length, surpassing the Osman Gazi Bridge. Nevertheless, the Osman Gazi Bridge remains a crucial artery in Turkey's road network, supporting economic activities and offering convenience to millions of commuters and tourists. Its role in reducing travel times and connecting key economic regions has proven invaluable, helping boost the region's connectivity and development. The Osman Gazi Bridge, named after Osman Gazi, the founder of the Ottoman Empire, stands as a symbol of Turkey's infrastructural ambition and engineering prowess. It dramatically shortens travel times between Istanbul and the western provinces, slashing the drive from Istanbul to Izmir from 10 hours to just about 4 hours. The bridge, part of a 421-kilometer-long motorway project, also connects Istanbul's bustling Sabiha Gökçen Airport to the eastern province of Bursa in less than an hour. This feat of construction not only addresses traffic congestion, but also enhances Turkey's economic and social connectivity. The Osman Gazi Bridge is a suspension bridge spanning the narrowest point of the Gulf of Izmit. Its total length is 2.7 kilometers, 8,858 feet, making it the fourth longest suspension bridge in the world when it was completed. The bridge's central span, measuring 1,500 meters, 4,921 feet, adds to its distinction as an engineering marvel. The design of the bridge balances strength with elegance. The aerodynamic profile of the deck edge lends it an appearance akin to an elegant ribbon floating above the Gulf. This feature not only contributes to the bridge's aesthetic appeal, but also plays a functional role in reducing wind resistance, ensuring stability, and enhancing its structural integrity. As vehicles cross, the bridge offers sweeping views of the landscape and the surrounding hills, with the transparent nature of its design adding to the visual experience. The bridge is a key part of a larger motorway project that has revolutionized travel times between Istanbul and Turkey's western provinces. Before its construction, drivers needed to loop around the entire Gulf of Izmit, a journey that could take hours, especially during peak travel periods. The combination of the Osman Gazi Bridge and the newly constructed highway cuts this once lengthy detour, reducing the distance and travel time significantly. Now, the journey from Istanbul to the western city of Izmir, a critical route for commerce and tourism, takes only 4 hours, compared to the previous 10-hour drive. Furthermore, the driving time from Sabiha Gökçen Airport to Bursa is less than an hour, making regional travel more efficient for commuters, tourists, and logistics services alike. The Osman Gazi Bridge was constructed as part of a massive infrastructure project aimed at boosting Turkey's transportation network. This ambitious endeavor began with a groundbreaking ceremony in 2013, following years of planning and collaboration between local and international companies. The Turkish government awarded the construction contract to a consortium of 5 Turkish companies and an Italian construction giant, forming the NOMAYG JV, Nural, Ozalton, Makyal, Yüksel, Gökay, and Astaldi. The joint venture opted for a build-operate-transfer model, allowing private investment and expertise to drive the project forward. The design and construction were primarily carried out by IHI Infrastructure System Company, a Japanese firm with a history of building major suspension bridges. IHI handled the detailed structural and seismic design, ensuring the bridge could withstand the active seismic conditions of the region. Danish engineering firm COWIAS collaborated on the bridge's aesthetic design to ensure that the final product blended well with the local landscape and met international engineering standards. The Osman Gazi Bridge represents a monumental achievement in modern engineering and infrastructure development. From its conception in 2009, through design and construction challenges, and ultimately to its completion and inauguration in 2016, the bridge stands as a testament to Turkey's commitment to advancing its transport infrastructure. The Osman Gazi Bridge is not only a significant engineering achievement, but also a pivotal component of Turkey's transportation infrastructure. By dramatically reducing travel times between Istanbul and Western Turkey, the bridge and the accompanying highway have unlocked new economic opportunities and enhanced social connectivity. The project not only shortened the distance between major cities, but also showcased collaboration between international and local companies, combining their expertise to deliver a project of immense scale and significance. Its strong yet elegant design adds a scenic dimension to everyday travel while meeting the region's transportation needs efficiently. The Braehead Rail Bridge is a significant infrastructure component located near Bargeddie, North Lanarkshire, Scotland. It forms a key part of the M8, M73, M74 motorway improvements project, which aimed to enhance transport connectivity, traffic flow, and road safety across central Scotland. This multi-million-pound initiative was launched by Transport Scotland to upgrade major motorways and improve journey times around Glasgow and the wider region. The Braehead Rail Bridge was constructed to carry the M8 motorway over the Whifflet railway line, a critical rail line that links Whifflet and Coatbridge Central. Located near Bargeddie, this bridge is a crucial link between Glasgow and Scotland's Central Belt. The overarching M8, M73, and M74 improvement projects aimed to ease traffic congestion on the busiest sections of the M8 motorway, notably in the stretch between Bayleaston Interchange and Newhouse, a notorious traffic bottleneck. The construction of the Braehead Rail Bridge involved advanced engineering techniques to minimize disruption to the existing road and rail networks. Due to its location spanning an active rail line, the bridge's development required careful planning and execution to ensure the continuous and safe operation of trains while the work progressed. The bridge was engineered to provide additional capacity and improve safety. Key design elements included reinforced concrete beams to carry the weight of motorway traffic efficiently, a prefabricated superstructure to minimize on-site assembly time and lessen the disruption to rail services below, heightened safety barriers and parapets to protect vehicles on the motorway, integration into the M8, M73, M74 motorway improvements project. The M8, M73, M74 motorway improvements project was a massive undertaking designed to enhance the entire motorway network around Glasgow. The project, completed in 2017, targeted three key areas: the construction of a new section of the M8 motorway between Bayleaston and Newhouse, upgrades to the Wraith interchange at the junction of the M74 and A725, and improvements to both the M73 and M74 motorways. The Braehead Rail Bridge was a core element of the M8 upgrades, providing essential connectivity and alleviating congestion in an area critical for Scotland's economy. The new infrastructure offered improved journey times, more reliable connections, and better safety features, fulfilling the objectives of the motorway improvements project. The completion of the Braehead Rail Bridge significantly enhanced the accessibility of the M8 motorway and increased the capacity of the road network around Glasgow. The Linkbelt 248 HSL is a 200-ton, 181.44 MT lattice crawler crane that excels in heavy lift applications with precision and reliability. It features a maximum boom length of 300 feet, 91.4 meters, and a robust lifting capacity, making it a versatile machine for bridge construction and similar projects. The crane is engineered for efficient setup, maneuverability, and optimized safety with modern load monitoring and control systems. In Phil Campbell, Alabama, the Linkbelt 248 HSL was recently used by Wright Brothers Construction, Inc. to successfully lift and position massive bridge beams for an overpass project. This project required the lifting of 135 featuring 41.1 meters long bulb T-beams, each weighing approximately 120,000 lb. 54,431 kilogram, 120 featuring 36.5 meters into the air. Bulb T-beams are crucial for bridge construction due to their enhanced load-carrying capacity, and handling these requires precision and high-capacity lifting equipment. The Link-Belt 248 HSL demonstrated its strength and flexibility, working with a 248 H5 configuration to achieve the required height and capacity for this challenging task. The 248 HSL's lattice boom, combined with its well-designed counterweight system, allowed for stable and controlled lifting, ensuring that each beam was accurately placed. This level of precision and capability was critical for the project's success, given the beam size and weight, as well as the need to coordinate multiple crane movements on-site.